Hope it is visible. The PPT.
Yes, ma'am, it is.
Okay, so we are at what should be done slide, right? Okay, so let's start today's class. Good morning to all of you. Um, we are discussing the shell and tube heat exchanger design, and in the last class we have discussed the complete design procedure with the detailed explanation of each step. Okay, how to consider each step, and if design will not uh, be in a feasible range, how to bring it to the feasible range. Okay, what should be done to bring the parameters in feasible range. Parameters means overall heat transfer coefficient and pressure drop. If that is within the permissible limit, within the acceptable limit, we can have the valid design, right? So that we have discussed, and we have seen that to bring that these parameters within the range, uh, where I can make the change in tube side and shell side. Okay, so that you can consider, and uh, to illustrate the design procedure further, I will take a detailed example of this shell and tube heat exchanger. And as I told you that when we consider the design of shell and tube heat exchanger, or let's say other heat exchanger as well, we need only 5 parameters through which we need to start the calculations, right? So if you see this example, it is like we need to consider following duties, following parameters to design a shell and tube heat exchanger, and the parameters are 21,000 kg per hour of benzene which is available at 90 degree, and that should be cooled to 30 degree. So 90 degree to 30 degree, and that is inlet and outlet temperature, and this is the flow rate. So all what we can say, all parameters for one fluid we usually know. Okay, and second fluid we are having is water with 60,500 kg per hour, and which is available at 15 degrees Celsius. We need to calculate its target or its final temperature. Okay, pressure drop, when we say pressure drop of 1 bar is permissible on both the side, like shell side as well as tube side. Okay, so this is the problem. We need to start the calculation from the very basic thing, that we need to find out the heat duty. Okay, so you can keep in mind the flow chart which we have discussed in the last class. So you can keep on uh, like you can follow the steps one by one which are available in that flow chart, and here we are calculating the parameters involved in that flow chart. Okay, so the first we need to calculate is to find out the heat duty. Okay, and to find the heat duty we need specific heat of the benzene. Benzene is the fluid, is one fluid, and water is another fluid. Okay, so we will start with benzene because we know a terminal temperature for that, and we need to collect Cp value, viscosity, and other properties which we usually consider at average temperature. Okay, so benzene we need to start with 90 in inlet temperature, 30 outlet temperature. So 60 is the average temperature, and 140 degree Fahrenheit the temperature, average temperature we consider for benzene. Okay, now if we need to calculate the duty, we need to find out Cp value. Okay, so always keep in mind that you need to start with the fluid where in both inlet and outlet temperatures are known. Okay, so this is the chart where we need to consider the specific heat of benzene. And if you see the benzene available over here as 23 number. Okay, this table, this what we can say graph we have discussed in the last class also. So if you see benzene, it is corresponding to 23 number, and 23 number if you locate over here, you can find 23 is this, right? 23 spot you can locate over here. Okay, next thing is we need this scale where average temperature is available. So average temperature for this case is 140. Okay, so if I consider this is to be like 100, then this should be 150 and then 200, like that. Okay, so you can get this uh, one 140 will be around here. Okay, and that spot you can locate from here following this 23. Sorry, from here you can start. Okay, then following 23, wherever it will cut this. Okay, so that you can measure by scale. So wherever it will cut this right scale, that we consider as the specific value of sorry, value of specific heat. Okay, so if we see the value, that will be around 0.44 calorie per gram degree Celsius. That you can, if you see the average temperature and 23 spot, you can see the value at 0.44. Okay, and please try to see the value as accurate as possible. Okay, slight variation because you are seeing from the graph, so slight variation may be acceptable. Okay, like 0.44 is there, so 0.43 like that, but not much difference. And when you read this specific, or what we can say, property table, uh, you need to be very like accurate to see the values. So here the value we have 0.44, that we have converted in kilojoule per kg degree Celsius by multiplying 4.187, that you know already the conversion of calorie to joule. Okay. And now I'm having this specific heat, inlet and outlet temperature and flow rate of benzene. So heat duty we can calculate for benzene. This is 21, this should be 21,000. Yes, be 21,000. Please correct this. And uh, this is 0.44 into 4.187. No need to consider 8. Okay, so just to make all these corrections over here. And 60 degrees Celsius, that 90 to 30 it is moving, therefore. So total 644.8 kilowatt heat duty we need to consider in design of shell and tube heat exchanger. Now once I am having this heat duty, we need to find out unknown parameter of second fluid. Second fluid over here is water. Its inlet temperature is 15, outlet temperature we need to calculate. So for in case of water, that is easy to find out CP value. Okay, because everybody knows it, 4.187. Okay, if you consider this CP of water, that you can see over here 4.187, and considering this we can make the energy balance, and temperature you can obtain. Outlet temperature of the water is coming as 24.16, and when I am considering this CP value, what is the procedure which we have discussed in the last class related to this value? Like, if you have any fluid for which CP value is not known, okay, CP value is not known, so that CP value um, you need to assume any value. Okay, you need to assume any value of CP, make the balance, calculate this outlet temperature, and then this outlet temperature and this inlet temperature, for which you will make the, you will calculate the average value, and at that average value you need to see the value, specific heat value you need to find, and then for that specific heat you need to compare with the assumed value. I hope you are getting my point. And this procedure will keep on repeating till I am having equal CP values in two consecutive iterations, right? So in that way you can do, but in case of water, that is it is everybody knows it, okay? So that there is no not required to have these iterations. However, if you want to check for this outlet temperature and inlet temperature, you make the you calculate the average temperature, and then at that average temperature see the CP value from the chart, which will coming around 4.187. okay? So in case of water there is no difficulty, but for a different fluid it is quite tedious task to get the CP, get the correct CP value, okay? And another point which I want to make over here, like here temperature is 24.16. now this temperature of water, this is applicable only in the case of water, okay? This temperature of water should be less than 40 degrees Celsius, okay? This condition you need to check if you are using water, okay? And because uh, water has certain specific tendency, like when we increase the temperature of mm, water, okay, solubility increases, right? When we increase the temperature of uh, water or other fluids also, solubility increases. Now in the case of water, what will happen, that after certain time, after certain temperature, the solubility will start decreasing, okay? And that temperature is beyond 40 degrees Celsius. So what will happen with this solubility will decrease, okay, which will precipitate the material, or we can say the component available in the water, specifically the hard material, okay, hardness of the material like calcium ion, magnesium ion, or all these. So this solubility solubility decreases beyond 40 degrees Celsius, and when you work on the system more than 40 degrees Celsius, the scale formation will be significant, okay? And you need to go for regular maintenance in the system, and if you consider this water, what how you are considering this water. Let's say this water exit temperature is 24 degrees Celsius. Once it exchanges the heat with this with benzene, after that we need to lower down this temperature when it is entering the heat exchanger network, sorry, heat exchanger again. I hope you are understanding. So we need to bring 24.16 to 15, because then only it will enter into the heat exchanger. So this water will flow in a loop, okay? Loop, one side of the loop would be the heat exchanger, second side of the loop would be the cooling tower, where water enters at 24.16 degrees Celsius and exits at around 15 degrees. So the cooling tower, cooling water, what we can say, tower, in that case, if your temperature will be more, obviously it will cool down. There is no difficulty in cooling, but it will what we can say, damage the equipment significantly, or appreciably, when we consider temperature more than 40 degrees Celsius. So please keep this in mind. Everywhere you are using the water, the outlet temperature should be less than 40 degrees Celsius. That you need to check. Now if it is coming more than 40, what you have to do, you need to change the flow rate, okay? This flow rate is given, but you can change this flow rate, okay? But the temperature should not be should not exceed 40 degree Celsius. So this is a few things which you need to keep in mind. Now next step, if you see the flow chart, next step was to collect the physical properties. Cp value we have already calculated, and for both the fluids you know both the temperature inlet and outlet. Okay, now you need to calculate the average temperature of both fluid and collect other properties, okay, for which iterations are not required because you already know the temperature. You simply need to see the values of the properties. So this is a specific heat which we have already discussed. Okay, so average temperature of water you need to calculate, which is coming as 19.58 and which is 67.24 degree Fahrenheit, and Cp value that you know already, that we have already discussed. uh, Yes, so what is done over here, if you see, we have seen the Cp value at average temperature, which is coming this only, and this taking 24.16 as outlet temperature, Cp value, which is equal to the assumed value. Therefore you can keep 24.16 the exit temperature of the water. Okay, but this type of iteration you need to do when you have other fluid than the water. Okay, so we have average temperature of both the fluids, so we will collect other properties. Other property means the first of all we will see the thermal conductivity. Specific heat you have already calculated. Okay, and there is no need to go that much value for after decimal. Only 2-3 places are sufficient. Okay, thermal conductivity, if you see for benzene, its average temperature is 140. If you see, this is for benzene. Here it is given at 86 degree Celsius, degree Fahrenheit, and when 140 degree Fahrenheit. So 0.087 BTU per hour fit degree Fahrenheit. That value you need to collect from the table which we just have discussed, and then you need to use this conversion to bring it to the desirable unit. Okay, so that should be in like 1.5 into 10 to the minus 4 kilowatt per meter degree Celsius. So that is the thermal conductivity of benzene. Okay, sorry. Mm. Now when we are considering the viscosity for benzene, if you see this xy value we need to collect from this table. So it is like 12.5 and 10.9 for benzene. Okay, so you can 12.5 if you can see over here, and 10.9 somewhere here you will have the value 12.5 like this. Just a moment. 12.5. Somewhere here you can locate this, and average temperature if you are considering, that is 140 for benzene. You need to draw a line following this point, and wherever it will cut this, that value you need to choose as uh, viscosity in centipoise. If you make the straight line, okay, that value as 0.38. That value will come as 0.38 centipoise. Okay, sorry, this is written in wrong way. C should be small and P should be capital, centipoise, right? So when we convert this, it is 0.38 into 10 to the minus 3 kg per meter second. That is the viscosity, and density you may be given, or you can see from the table, and that table I will share with you. Okay, so in this way you can collect the properties of benzene, and Similarly, you need to collect the property of for water, specific heat we have already seen. Thermal conductivity, if you can see, average temperature I am having is 67. Sorry, 67.24 average temperature of water. Where it is here. So average temperature for water at 32 degree Fahrenheit, 100 degree Fahrenheit and so on, the values are available over here. We need to consider 67.24 in between these two, so we can go for the interpolation considering a straight line, equating the straight line expression. I hope you understand the interpolation, extrapolation and all. So we can have this 67.24 minus 32 by 100 minus 32, because in between these two we need to iterate. So x value you can calculate from here, and that you can find as 0.3534, and you can use the conversion to get the value. So it is coming as 0.61 watt per meter degree Celsius. Okay, viscosity for water, you know already, it is when we consider for water, it is 1 centipoise, and that is equal to 10 to the minus 3 kg per meter second. Density of water you can choose like this, or you can say take 1000, something similar. In the similar way you can take the value. Okay, so that is about the property collection. Actually, when we consider the when we go for the design, you can also find out viscosity, find out properties wherever it is required. Okay, always it's not in the beginning only you need to find the properties, but CP value you need to calculate, you need to find first. Okay, other property you can find wherever that it will be required, but in the same line which we have discussed. Okay, just 1 minute please, huh? I will continue. Okay, so right. So in this way we can find out the properties of the fluids. Now next step is to find out LMTD. Okay, LMTD and true LMTD. So LMTD, when we are considering, that should be here we need to assume the passes in heat exchanger, and initial gas we can consider as 1 2 pass, one shell and 2 tube pass, and we need to consider counter current flow. Okay, so LMTD you can find like this, and once I'm having this LMTD, we can calculate R and S value from uh, from the given expression which we have discussed in previous classes, and this based on this R and S you can find out FT value from this equation. Okay, FT value actually you can find out from the graph also. Okay, but for 1 to govern 1 to expression of FT is already given. Okay, so we will not use the graph, we can use this equation, because graph may give variations in values, but that expression will give only one value. So if you consider R and S over here, you can find FT as 0.9163, which is coming 0.75. It means our assumption is true. What assumption? Assumptions of 1 2 shell and tube heat exchanger. One shell will be sufficient to accommodate this temperature variation. Okay, if Ft value is coming less than 0.75, you need to consider here 2 4. Okay, so it should be like 1 2 is sufficient for us. So Ft value we have obtained, LMTD we have already calculated. So true delta T mean is coming as 31.48. Okay, and then we can find out, the next step is to find out heat transfer area, but for that you need to consider this U naught as the assumed value. Okay, so you need to assume the overall heat transfer coefficient. So here I am having the process fluid as benzene and service fluid as cooling water. Okay, you can use this chart. Um, So actually for this to see the value for overall coefficient, we have considered this in the this category paraffin, though it is not paraffin, but we are considering this because if you consider this heavy organic, it is also not fall in that category, so we can consider this. Okay, so uh, if you consider this paraffin, you can consider this middle point. You can consider the middle point of this, which will be like this. And cooling tower water, if you are considering, it is varying from this to this, so middle value you can consider like this. Okay, so you need to draw the line while matching these 2 points like this. It is not a straight line, but if you will draw the straight line, you will find the value of overall heat transfer coefficient as 575, and this you need to denote as assumed value. So you are already having delta T true value, U naught value, and this area you can calculate. It is the simple equation. Okay, so total heat transfer area you can consider as 35.62. Okay, now next step, if you remember, the next step is to find out the uh, number of tubes. Okay, so when you are considering number of tubes, you need to consider the area of one tube. Okay, and for that you need to consider the dimension of tube. Okay, so dimension of tube, when we are considering, sorry for this line, it is that I think we can erase. Okay, so as I have told you that to consider the better or what we can say, the optimum diameter of the tube, it will fall in the range of 16 to 25. Okay, 16 to 25 is the optimum range, and total if you see, it is 16 to 50. Okay, so we need to consider value between 16 to 25. So if you see this 3 by 4 inches, if you convert that into mm, it is coming as 19.05. So we can start with this value. Okay, and secondly, we need to choose a BWG value, and as we have discussed previously that this BWG value should be chosen from the middle. So we can choose 15 BWG value or 14 BWG value, like that. So I have chosen 15 BWG value. So for that, ID of the tube should be 0.606. Okay, so OD we have chosen as 3 by 4 inches, 19.05. This should be 19.05, I think, not 0.65. This is 0.75 into 25.4. Yes, 19.05 it should come. Okay, so in this way you can decide the tube OD and ID of the tube corresponding to 15 BWG value. Okay, now this is the diameter. How I can choose the length? If you remember, length are varying in like different values like 6, 8, 12, 16, 20 and 24, I guess. Okay, all these values are standard values. You cannot take any value in between this. Okay, so you need to start the assume the middle value from this. So let's say you can start with 16 feet. You can start with 12 feet also, there is no problem, but it is preferred to take middle value 12, 16 like that, not the edge value, because their iteration would be more. Okay, so if I consider this as 16 feet, conversion of that into meter will be 4.8768, and this is the length we are considering, and now we need to calculate area of one tube. Area of one tube, when we are considering pi d naught L effective, we need to consider pi d naught value is there already, d naught value. L effective, effective means you need to deduct the section of the tube which is inside the tube sheet, which will not participate in heat transfer, right? So in that way, how we need to choose the correct thickness of the tube sheet? Okay, tube sheet thickness should never be less than 25 mm, that we have discussed in construction details. Okay, so that you can recall 25 mm at least tube sheet thickness should be. Okay, now if I consider OD of the tube, which is in this case is 19.05, if OD of the tube is more than 25, okay, if OD of the tube is more than 25, you need to consider OD of the tube as thickness of tube sheet. Let's say it is 30, 30 mm tube you are considering, tube sheet thickness should also be 30. Otherwise it is 25. Okay, so when I am considering 25 mm both sides, 50 mm we need to deduct from the total length. Though you can say that 50 mm is very less, yes, that's true, but it will affect the number of tubes you can calculate. Okay, so L effective should be the total length minus twice of tube sheet thickness, and which is the area of one tube is coming as 0.2891. Okay, in that way you can calculate the tube, that is the tube OD. Sorry, that is the area of one tube. Now once you are having the area of one tube, you can find out total number of tubes as 123.09. Okay, now in this case uh, you should keep in mind that number of tubes should always be even. It will never be odd, because we are considering at least two passes in tubes. Okay, so it should be completely divisible. Okay, so 123.09 is coming, so we need to consider 124. Let's say if it is coming as 124.09, or let's say 124.3, let's say, in that case what value of total tube you need to choose is 126. Okay, because 124.3 is there, your next value is 125, which is not an even value, so we need to consider next even value, that is 126. I hope you are getting my point. This will change further also, that we will discuss. Okay, so for two passes 62 tubes per pass should be there. Okay, so once I'm having this number of tubes, we need to proceed for shell dia calculation, and for that shell dia we need to calculate bundle dia, and for bundle dia we need this K1 and N1 value. Okay, so if you can see this, I'm having this 2 tube passes. So this, well, we can choose why not this value we have chosen. Why only this? Because we are assuming triangular pitch. Okay, if you recall the last class, triangular pitch will be sufficient for many designs of shell and tube. So we can start with that selection only, that arrangement only. Okay, so here I am considering triangular pitch, and K1 and N1 value you can see uh, from this chart. So once I'm having K1 and N1 value, we can proceed for the bundle diameter calculation. This is the expression where NT is total number of tubes, not number of tube per pass. Please keep that in mind. Okay, NT is total number of tube. So considering this dB, we can considering all these value, we can find dB as 0.318. And to calculate shell dia, you need to consider clearance along with bundle dia. Bundle dia we have already calculated, and here we need to calculate, we need to see the, what we can say, the clearance, and that clearance will depend on the type of heat exchanger. So this is the time you need to choose the right heat exchanger. Okay, right heat exchanger, if the exit uh, temperature available in heat exchanger, whatever would be the fluid, if it is less than or equal to 90 degrees Celsius or so, you can choose fixed tube sheet. Okay, if you are given that fluid is clean in nature, okay, fluid is clean in nature, in that way you can consider U tube. Okay, if temperature is more than 100, more than 90 degree. Okay, if temperature is more than 90 degree and fluid tendency is clean, okay, you can go for U tube. Okay, if fluid tendency is not clean and temperature is more than 90 degree, you can choose internal floating head or external floating head, but it is preferred to choose external floating head. Okay, because in that case clearance would be lesser, and so shell dia would be lesser and the less cost will be involved. However, if you are dealing with toxic fluids, okay, if both fluids are toxic, one you need to allocate to tube side, another should be in shell side. In that case, internal floating head, or we can say pull through floating head, is will be preferred. Okay, so here I'm having fixed tube sheet heat exchanger, and diameter, if you are considering 0.318. Okay, 318 point, this should be 0.3, and somewhere here you can have the value like this. Okay, so something here you can get the value, so that value you can choose, you can consider as 11 mm, 11 mm, and then we can have this shell dia simply by adding bundle dia with clearance. And here, once you have this shell diameter, you need to check the value. Check the value in what sense? Check the L by D ratio. Okay, whatever length of the tube you have chosen, the same of length of the shell will be considered. Okay, so length you have chosen as 4.87 meter, and this diameter you can shell dia you have calculated as 0.329. So this should be the ratio is coming as 14.827, but the optimum range is 5 to 10. Okay, so it means you need to reduce the length. Okay, you need to reduce the length of the tube, which you have considered previously 16. Now you can choose the lesser value, and that should be 12, which is available in the standard. Okay, not 18. Okay, sorry, not 14 or 15 or 13. Okay, next is 12 only. So 12 you need to choose. Again, you need to calculate number of tubes based on effective length. So now number of tubes are coming as 166. Okay, even value you need to choose, that I have already discussed. And this number of tube per passes, 83 tubes per pass you need to choose. And K1 and N1 will remain same because it will not it does not depend on the bundle dia. Bundle dia depends on that. Okay, so K1 and N1, when it will be affected when you are changing the passes, tube passes, or when you are changing the pitch. So both I am considering the same. So K1 N1 will be same. Bundle dia would be like 362 and point 362. So it will change the clearance also. So now I'm getting clearance as 12 feet ds, but shell dia you can calculate, and then we can find out L by D ratio, which is now coming as 9.75, which is less than 10, between 5 to 10. So 12 feet is the correct length of the tube, or we can say length of the exchanger. Okay, length of the exchanger means where tube and shell is available, not the covers. Okay, covers will have some standard that will be added. So once you are having with this L by D ratio, you can proceed for next uh, step, that you need to assign the fluid to tube side and shell side, because we need to calculate the heat transfer coefficient. Okay, for this you need to require flow of in shell side and tube side, for which you need to allocate the fluids to shell side and tube side. And how you can choose that? One fluid you have benzene, another fluid you have is the cooling tower. So if you remember the priority order, the first one is the corrosion, okay, in tube side. Second is the fouling. But for corrosive, if fluid, it is mentioned that fluid has corrosive tendency, you can inlet that in the tube side, even if fouling of that tube fluid is lesser. Okay, but in that case corrosion tendency of the fluid is not mentioned. So we will proceed for second order, second parameter in priority order, and that is fouling factor. Okay, so we will consider fouling factor of water and benzene. If you consider cooling tower, this we have the fluid, so 3000 to 6000 you can consider. And if range is there, we need to choose the average value, so that should be 4500, right? And benzene you can consider in organic liquid, so it is coming as 5000. This is coefficient. Dirt factor would be just reverse of that. Okay, so you can consider the fouling factor for this what we can say, the fouling factor for this is 450, sorry, fouling coefficient is 4500. For benzene it is 5000. So if it is lesser than this what we can say, for water, so water should be allocated to tube side, not the benzene. Okay, however difference is less, but even you need to choose the value between the what we can say, you need to choose the value for different fluids. Okay, so based on that we can allocate the water to tube side, and benzene should be in shell side. Okay, now if I'm having this, we need to calculate tube side heat transfer coefficient and shell side heat transfer coefficient. So first of all, we will proceed for tube side heat transfer coefficient, for which you need to calculate the velocity. Okay, and that velocity should be in the permissible limit. Okay, so we are having this cross sectional area, uh, of one tube. Okay, and if you consider 15 bwg value we have chosen, corresponding to that inlet id of the tube is 0.606. That should be in inches, so we need to convert that into meter, and you can see the value obtained in meters, meter square, sorry. Okay, and area per pass, because 166 tubes we have calculated, and then you can consider this what we can say, the number of tubes per pass, and which is coming as 83 right now. So this is the area per pass. Volumetric flow, you are already aware, you know the density, so you can simply calculate the velocity. I don't need to explain that, you people are already aware of that. But my point is, what velocity you are getting is 1.09 meter per second. If instead of water you were using the fluid, that will be okay, because it should be 1 to 2 meter per second. But in case of water, it should be 1.5 to 2.5 meter per second. Okay, so if you recall the last class, there we have seen that uh, how we can bring the velocity, or how we can increase the tube velocity. That would be increased by considering, by increasing the passes. Okay, so which pass? The tube pass, not the shell pass. Okay, so we are considering 1-2 shell and tube heat exchanger. Now we need to consider 1-4 shell and tube heat exchanger. Okay, and until unless shell number will not change, FT value will not be affected. Okay, FT value and true LMTD and this A naught area, all these value will remain same. Okay, so tube length and area of the tube also remain same, because 12 feet we have fixed. And if you recall, we have considered 166 tubes. Okay, but if you divide this 166 by 4, it will not be a complete number. So we need to increase the number of tubes, that should be completely divisible by 4. So we will, instead of 166, we will consider 168. So 42 tubes per pass we need to consider. K1 and N1 value. Okay, if you see the bundle diameter, it depends on K1 and N1, and which depends on the passes, tube passes. Okay, so instead of 2 passes, we will consider 4 pass, and corresponding to that K1 and N1 value you can see from the table, which we have discussed few slides back. I don't need to show that table again and again. You people, I hope you have already that idea that which table I am talking about. So dB should be the bundle diameter, and that you can find as 0.384, considering revised number of tube, that is 166. Clearance you can obtain further, then shell dia would be this. And once I'm having the shell dia, again you need to check the L by D ratio. Okay, so L by D ratio should be coming as 9.2. Okay, so still 12 feet will be acceptable. If it is not, you need to again iterate. Okay, so all these things will give you uh, many iterations, and that will depend on the condition we or the what we can say, assumptions we are taking. So 42 tubes per pass, one area of one tube you have already calculated, so you have area per pass, and then you can see the velocity, it is 2.159. Okay, so when we consider the initial velocity, it was coming as 1.09. Okay, so while in just making the pass double, we should consider velocity should be just double to that. Okay, but if you consider 1.09, the double of that should be 2.18. Okay, but velocity we are getting as 2.15. Okay, the reason will be the number of tubes we have changed. Okay, so don't consider, don't just double the velocity. However, if number of tubes are not changing, if it will remain 166 now also, then you can consider you can simply double the velocity. Okay, so now 2.156, which is falling between 1.5 to 2.5, so this velocity should be acceptable. Okay, once I'm having the velocity, we can calculate the heat transfer coefficient. And if you remember the last class, we have discussed that heat transfer coefficient for water, it has a specific expression which is shown over here, 4200 and all. Okay, so ut is the tube side velocity, T is the average temperature of the water, and Di is the ID of the tube. But you need to consider one thing in mind, that this ID should be in mm. Okay, don't need to match the units because these are empirical expressions. Okay, not the method, what we can say, conservation based equation. Okay, so these equations are derived from experiments. Therefore, you need to consider this Di in mm. This should be meter per second. This should be degree Celsius. Okay. So if you consider this, you can find out heat transfer coefficient in tube side as 7822.564, and that should be denoted as Hi. Okay. Now we will proceed for shell side heat transfer coefficient, and for shell side you need to decide the plate spacing. You need to decide the baffle spacing and baffle cut. Okay, so baffle spacing, if you see, the whole range varies from 0.2 to 1 into ds. Okay, but optimum should be 0.3 to 0.5. So we will choose 0.3 as initial guess for baffle spacing. So 0.3 into ds, the ds we have already calculated. So this much baffle spacing you have obtained. We need to calculate the cross section, cross flow area, not cross sectional area, cross flow area, which we have discussed in the last class. And here we are designing the shell and tube heat exchanger using Kern's method. Okay, which we have discussed in the last class. Okay, and for this Kern's method, we need to find out this cross flow area, which is coming out like this, and we can calculate the velocity considering the flow mass flow rate of shell side, which is for benzene. Okay, so you can consider velocity as 0.73627, and it is falling between 0.3 to 1. Okay, so here also you need to check the value. So 0.3 to 1 is the what we can say, the recommended range for velocity in shell side. Okay, please refer to the basic design parameter lecture. Okay, there we have discussed the tube side and shell side velocity. Next, you need to find out the equivalent diameter. I hope all these steps, which are one after the another, that you people are already aware, which we have discussed before. So equivalent diameter for triangular pitch you need to consider, and this is coming as 13.537. Okay. Now, if you consider this equivalent diameter in shell side, it is 13.5 mm. Okay. Now you consider the ID of the tube. ID of the tube corresponding to 15 BWG value, it will come around 15 mm. Okay. ID, the tube side, whatever diameter we are considering, ID of the tube, it is 15, but the equivalent diameter in the shell is 13.5. Okay, why I am trying to connect these two value, ID of the tube and equivalent dia of the shell, to make you understand that tubes are placed so compact to each other that what we can say, the characteristic distance in the shell side would be lesser than that in the tube side. Okay, so however, if you see the shell diameter is significantly higher in the in comparison to OD of the tube. It is only 19 mm. Okay, but it is shell die is coming as around 400 mm. Okay, but the flow, what we can say, the characteristic length, or we can say the equivalent dia in shell, that would be lesser. Okay, I hope you are getting why what I'm trying to emphasize on. And once I'm having the velocity and that equivalent dia of shell side, we can find out Reynolds number, and we can find out Prandtl number if based on the property which we have collected in, I think, second step. Okay, so once I'm having this Reynolds number, we need to choose the right baffle cuts, and that should be 25 mm should be sufficient to start the calculations. Okay, so we need to find out this JH to find out the heat transfer coefficient. This is the heat transfer coefficient expression where JH we need to find. Okay, and JH you can find by this. Here I am having the Reynolds number. Sorry. So Reynolds number is coming as around 2.2 into 10 power 4. Okay. So if you see here, I am having 10 power 4 and this is 2. So 2.2 will be near to this, and this is the line of what we can say 25 baffle cut. So corresponding to this JH value you can obtain as 4 into 10 power minus 3. Okay, that you can see in this range, 4 into 10 power minus 3. So please be see the value from this graph very carefully, and all these graphs will be provided to you. Okay, now once I'm having this JH value, we can find out shell side heat transfer coefficient, which is coming as 1624.07, and that should be HO. Okay, here it is written as HS, but it should be HO. Okay, now once I'm having HI and HO, we have already collected the dirt coefficients, okay, for water and benzene. We need to find out overall heat transfer coefficient. All these value we know already, that HO, and this is HOD. Actually it should be HOD, dirt coefficient, not DHO. It is like we are multiplying D and HO, but it should be HOD. Okay, similarly the whole expression we have already discussed. Similarly you need to consider this as HID. We need to find this KW. KW is the material property. Okay, so thermal conductivity of the material, if let's say if you have chosen that carbon steel like that, so for that KW value should be 27, and that you can convert into required value unit. And once I'm having this, we can find out overall heat transfer coefficient as 773.4 watt per meter square degree Celsius. Okay, next step is to find out percentage error. Okay, but here if you see, percentage error is coming as 25.6, but there is one mistake from my side. Like here I'm having this U calculated minus U assumed divided by U assumed, because we are comparing with the assumed value. So this is coming as 773, and the assumed value was 575. So when you calculate the percentage error, uh, considering here you assume, it is coming as 34% or so. Okay, which is near to 30, but obviously it is higher. Okay, so we need to choose what we can say, we need to reiterate. Okay, to bring it overall heat transfer coefficient below 30 degree. Now to do that, because this is difference is not much. Okay, so instead of, if you recall the flow chart, there we have started with that, like assumed value should be replaced with calculated value, and you need to start with the heat transfer area calculation and all. Okay, but in this case, because difference is less, you can make other changes as well. Other changes means, like if you see the tube uh, tube side heat transfer coefficient, that is around 7800, but this shell side heat transfer coefficient, it is 1624. Okay, so if I reduce this further, we can have the overall heat transfer coefficient, because it will be majorly controlled by this value. Okay, uh, So instead of baffle, we need to reduce this. Okay, reduce this means we need to increase the flow area. So instead of baffle cut as 25, you can consider next value that should be 35, and you can increase the baffle spacing. We have chosen 0.3 into ds, you may consider 0.5 into ds. So like that you make the changes, and only doing that you will find variation in shell side calculation. Tube side calculation will not get affected. Okay, so however, if you assume the if you replace assume value with calculated, you need to change whole calculation from area. Okay, so if you do that, you can bring it to the permissible limit within plus minus 30%. Okay, so that part you can do on your own. I'm just moving ahead with this. Okay, however, ideally iteration is required at this moment. Okay, so in this way we can find out shell side heat transfer coefficient and tube side heat transfer coefficient and overall heat transfer coefficient. Okay, overall heat transfer coefficient, once you do the iteration, you will find in you will bring that in the permissible limit. Okay, however, next step I'm having is the pressure drop. Okay, pressure drop for tube side. Okay, pressure drop for tube side, I'm having 4 passes. ID of the tube that you are already aware of, ut you have already calculated. So you need to consider the Reynolds number to find out this jf. Okay, and this np would be 4. Okay, Reynolds number you need to find based on the velocity, and that is coming as 3.3 in 10 power 5, which is more than 2100. So it means you can use the turbulent region for that expression we have already discussed in the last class. Okay, or sorry, not expression we have discussed for heat transfer coefficient. For pressure drop, we have calculated the this expression based on graph. So jf value you can obtain now. So it is coming as 3 point something into 10 power 5, like that. Okay, so in that way you can find out the jf 3.3 times per 5. Uh, if you see this Reynolds number, right, you can use this graph. Three 3.3 somewhere like over here. Mm-hmm. Okay, so you can see this value and you can see this value from the graph. Okay, and once I'm having this jf value as 3.5 times or minus 3, from the graph we can calculate pressure drop, which is coming as 0.8478. Okay, and if you remember the problem, it is given like 1 bar is permissible at both the side, shell side and tube side. So here it is coming less than 1 bar, so tube side calculations are okay. And we will proceed for shell side. Shell side pressure drop, sorry, this should be delta ps shell side. Okay, Reynolds number for this you have already calculated based on us velocity in shell side, and jf you can see from this chart depending upon 25 baffle cut. However, if you increase the baffle cut, you need to choose the value of jf accordingly. So uh, I guess that you can see the value, but be accurate as much as you can. And here I'm having other parameters, so putting all the value over here, we can find out pressure drop as 0.057. Okay, atmosphere, and or we can say the bar. Okay, so which is also less than 1 bar. Okay, however, you need to consider mm, some fact or some factor over here, not factor, some fact, like if you are considering this is capital L, okay, this is not 1, this is capital L, which is length of the uh, shell, and this length of the shell will depend on the length of the tube. Okay, so please keep in mind when you are calculating pressure drop in shell side, okay, this L should be L effective. Here capital L should be L effective, okay, not the total length. However, when you are calculating the tube side, the length should be total length, not the effective length. Okay, so please keep this in mind. Tube side, you need to consider total length for pressure drop. Shell side, you need to consider effective length. The reason would be the tube side, because whatever part of tube is available in tube sheet, it will not participate to create friction in shell side. Okay, however, it will create friction in tube side. Therefore, in the tube we consider total length, and in shell we consider effective length. So that correction you need to keep in mind. Just one. Just 1 minute. Yes, if you see this 12 feet, it is coming as it is coming as 3.657. Okay, and for effective length, we have to reduce the twice of tube sheet thickness from the total length. So 50 has already been reduced here. So L is already effective over here. Okay, so for shell side pressure drop, you need to consider effective length. For tube side pressure drop, you need to consider total length. Okay, so in that way we can see that the the pressure drop of both sides should be in the permissible limit, and that we consider as validity of our design. Okay, some iterations I have already told you for tube side in between, so that you can, for heat transfer coefficient, sorry, so that you can do, and after that you should proceed for pressure drop calculations. Okay, so in that way you can design a shell and tube heat exchanger. Okay, I will tell you one, I will give you one problem to solve, and that you practice based on this example. Okay, so probably in next class or so I will provide the uh, so that another problem, and that problem you can do, and then we can discuss the doubts in this class only. Okay, I'll give some time to calculate, to design that, maybe for 2 3 days or so. Okay, so that problem I will tell you tomorrow, or I can email that also to Ziaul sir, and he will give you. Okay, so in that way you can uh, design the shell and tube heat exchanger only with Kern's method. Okay, based on Kern's method, this design is discussed. Okay, so we are having a little bit time, so I will discuss just after 2 minutes. I'll start after 2 minutes. Please wait. Huh? So let's discuss further. We have around 10 minutes or so. So this is in this way we can consider the valid design of shell and tube heat exchanger using Kern's method. And next method we have for design of shell and tube heat exchanger is Bell's method. Okay, actually when we consider the method, a different method in the last class we have discussed also that all these methods are designed or are made to design shell side. Okay, tube side, whatever method we have calculated in previous example, that will remain as it is. Okay, so when we are considering Bell's method, it calculates, just a moment please, sorry. Hello. Okay, sorry. Bell's method, when we are considering it, is it calculates shell side heat transfer coefficient and pressure drop, uh, considering effects of leakage and bypassing and use of sealing strips. So what these leakages and bypasses are, and what is the sealing strip, that all we have discussed. If you consider this Bell's method and the Kern's method only consider the flow through maximum cross flow area. Okay, flow through maximum cross flow area, which is at the, what we can say, at the middle, or we can say at the equator. Okay, uh, that is equator, it should be a middle. Okay, that we have also already seen in the last class. However, Bell's method considers other sections also. Okay, like cross flow zone is one, other zones we have window zone and all that we will discuss. It means that Bell's method counters much more parameters in comparison to Kern's, and therefore it gives more accurate design in comparison to Kern's method. But Kern's method is like, we can have that simple method, it gives reasonable results, but Bell's method is more accurate. Okay, so why we are not discussing Bell's method from the beginning? The reason being, this Bell's method has been developed over Kern's method. So Kern's method is the basic design, and over which whatever modifications are there, accordingly methods are given. So we will discuss in the same line, Kern's method first and then others methods. Okay, so when we consider Bell's method, as I have told you, it gives more accurate results. So it gives more satisfactory predictions of heat transfer coefficient and pressure drop in comparison to Kern's method. And heat transfer coefficient for tube side and pressure drop of tube side, whatever we have discussed previously, it will remain as it is. Only the shell side parameters will be changed. Okay. So before computing this, these parameters, required parameters for Bell's method, I should consider the streams which are involved in shell and tube heat exchanger. Okay, so here I am having shell side leakage and bypass streams or paths. Okay, so if you see, we have different nomenclature. One is stream A. Okay, if you see the stream A, this stream A basically, this is between the tube to baffle stream, or tube to baffle gap. So this stream A is called as tube to baffle leakage stream. The fluid flowing through the clearance between tube OD, okay, tube OD and tube hole in the baffle. Usually that hole in the baffle is like with sufficient gap so that it can smooth freely, it can move smoothly over the tube. Okay, so this stream A is this leakage stream, okay, between tube to baffle, okay, gap, between tube to baffle gap. So this is stream A. Next I am having stream B. Stream B is the what we can say, the cross flow stream. Okay, now if you recall the Kern's method only considers stream B, and that too only at the middle. Okay, however, this Kern's method considered the cross flow region from this baffle tip to this baffle tip. Okay, so stream B is the cross flow stream between two baffle tips. Okay, two consecutive baffle tips. I'm having stream C. Stream C is the bundle to shell bypass stream. Actually, stream C considers what? If you see this image, you can see that you can find the stream C is lying where it is very clear. Okay, but here you are saying that stream E is also in the same line. Okay, the difference is stream C is basically this region. Okay, whatever gap I am having, whatever clearance, you can say, whatever clearance I am having between shell diameter and bundle diameter. Okay, so stream C is the bundle to shell bypass stream. Why we consider this as bypassing? Because whatever stream fluid will be available there, it will not it will not participate in heat transfer, because these zones are considered as the, what we can say, the dead zones. Okay, so stream C you can find over here. However, stream E is the leakage stream between baffle and shell ID, between shell dia. So that is baffle to shell leakage stream, the flowing through clearance between edge of the baffle and shell wall. So here in this diagram, E and C both are looking same, but no, E is between baffle to shell and C is between bundle to shell. Okay, I hope you are getting my point. And after that we have another stream, that is stream F, and that is basically pass partition plate. Okay, so you can understand that pass partition plate we always consider in tube side, not in shell side. Okay, but wherever that pass partition plate will be available in tube side, the corresponding place in bundle should remain empty. Okay, there should not be any tube. So that will also be considered as dead zone. Okay, therefore when we consider the pass partition plate, uh, the in that region no tube can be placed in shell side. Therefore, according to pass partition plate, shell dia will increase. Okay, remember K1 and N1, which depends on the passes. Okay, so those pass partition plate, it is available in tube side, but it will affect the shell side flow also. Okay, so stream F we are considering in between this, as you can see. And Bell's method, when we are considering, apart from stream F, all these streams are counted in Bell's method. Okay, considering stream F in Bell's method, we have another method that we call as stream analysis methods. Okay, or we also call that as HT. I think HTRL method or so, but more precisely it is called as stream analysis method. So Kern's method will not count stream F, other streams it will count. Okay, so let's proceed further. When I'm having stream C, okay, if you consider the title, we are discussing leakages and bypasses stream, but only bypass is stream C. Okay, stream A, B and E, all these are considered as the, sorry, stream A and E are considered as leakage stream. Stream B is the cross flow stream and stream C is bypass stream. Okay, now as I have told you, that is it depends on the clearance between clearance between bundle and shell. So as this clearance increases, we have chances to accumulate more and more liquid there, which will not participate in heat transfer. Okay, therefore stream C is main bypass stream, and will be particularly significant in pull-through bundle exchanger. Pull-through bundle exchanger means internal floating head. Okay, remember that is the main drawback of internal floating head. Okay, so uh, this internal floating head or pull-through exchanger, if we are using, we need to uh, be more careful for stream C in comparison to other exchangers. Okay, so stream C can be considerably reduced by using sealing strips. So what these sealing strips are, where it should be considered, where it should be included, all that we will discuss when time comes. Okay, so that is about the different streams which we are considering in tube side, sorry, in shell side. Please wait for 1 minute, sorry. हाँ हाँ ठीक है. Okay, so in that way we can consider different streams, and considering all these, we will discuss the Bell's method. We will start discussion on Bell's method from next class. That probably tomorrow or so. I will let you know. Okay, so that is all from my side for today. If you have any confusion, any observation, you please share. Please discuss with me. Otherwise, that's all from my side. Thank you. So I hope no questions. If you have any question, you please discuss. So thank you everyone for your patience. We will discuss Bell's method further. Thank you everyone.